Okay, can I have your attention, please? We are going to start now. So this is tutorial 2 for ECE243. And the goals of the second lab is gaining more familiarity with assembly, because in lab 1 you practically had the program written for you. Learning good coding practices, that's a goal of all the labs. Seeing the difference between move instructions, loads and stores, and between signed and unsigned numbers, and different data types that you have in this machine, which are basically words, half words, and bytes. Starting with this lab, you will need to submit all your code to Blackboard at the end of the lab. I don't know if it's set up already, but you can go in there, and where it says lab 2, you submit the code. It's, if I remember correctly, one person per group only, and you have to submit all the files you have. Since there are 3 parts, you will probably have to submit 3 different files. Okay. So the objective of, there are 3 exercises. You have to go through a list of numbers and classify them between positive or negative. The list is in 3 formats. One is a fixed length list of 10 numbers. The second is a variable length array, which is terminated by a 0. You have to check every number and see whether it's a 0, and then you end there. And the third one is a linked list, where you have a pair of elements. One is the number, and the other one is a pointer to the next element. And as you classify them, you have to count them, put the counters in registers, and then write back to memory to 2 different arrays. One is the positive array, the other is the negative. Okay, so the next part, the difference between moves, loads, and stores. Does anybody know the difference? Moves, loads, and stores.
The move will transfer data between registers, while
Yes.
load and store is between registers and the main memory or hardware.
That's right. What do you mean hardware? Everything is hardware.
I/O interfaces.
Yes, yes, that's right. So for I/O interfaces, you want to use load I/O or store I/O in general. So what's the difference between registers and memory? Can anybody guess? Difference between registers and memory? Yes?
One you can actually do calculations and operations with, like with registers, whereas memory you can't do it directly.
Yes, that's one of them. The registers are typically, you have few of them, they are faster, and the indexing also changes. For memory you provide addresses, for registers you have a register number, which is generally something you don't operate on, but yeah, that's good. So move. Move, this machine, if you look carefully, doesn't have actually a move instruction. A move is implemented by add with an immediate of 0. Does everybody know that? In this machine, you do move. If you do move R1, R2, what you are doing is these 2 things are the same thing. Okay, this is just, you don't need a redundant instruction to do moves. The addition is free, or for our practical purposes free. So yeah, this instruction will copy R2 into R1. There is nothing to see here. The registers are always 32 bits. I thought I could change them. Okay, load and store. Load takes the address, which is in register R1, goes to memory, goes to that address. Here we can only see a small part of the memory, but it goes up and down quite a bit. And we'll load that register, put it into the destination register, which in this case is R2. There is nothing more to it. There is an optional 16-bit offset, which in this case is 0. We don't have anything before R1, but you can specify an offset. Goes to here, takes the value, puts it in here. Nothing there. This is the converse, which is a store. It's going to take whatever is in R5, which is 1010 in hexadecimal, add 2 to it, because there is a 2 in the instruction, and then store the value of R2. It's a store half, which means the minimum alignment is 2, not 4. There are 3 variants of the instructions. One is for words, other is for halves, which is this one, another is for bytes. Since we are storing a half word, we only need 2 bytes of alignment, so that's legal. Okay? If we instead wrote 1 R5, that's not a valid instruction. It will do something undefined. It's going to take the lower 16 bits of the register and put them into memory. Always the lower 16 bits of the register. Is that clear? Everybody understands what the H is for in the instruction? Tells that we are using 16 bits. It's going to go there and put the value there. Since this is letter endian, this is byte, so to speak, 0, 1, 2, and 3. Since we are starting from 2, we are starting from here and going up. Does that make sense? Is that clear to everybody what's happening there? If instead of writing 32 bits per entry in this table, we divided this into 2 16-bit halves, then we will be putting this in the next entry, so to speak. Right? So the direction of bytes in the memory is like this. This you should have seen in the first lab. Okay. Sign extension. So for the load half word and load byte instructions, there are 2 variants, the unsigned one and the signed one. Only for those variants. Can anybody tell me why? Or is it too soon? Okay. We have 2 variants, load half, the normal one, which is signed, and load half unsigned. Okay? These are going to do different things on some situations. Let's see what the first example was. The first one is unsigned. It's going to take the lowest 16 bits, put them into the register, and zero out the upper 16 bits. Always zero out. The registers are always 32 bits. So if you are reading 16 or 8, you need to convert them. Is that clear? If you are, yes?
I just have a question about the signed one, load signed word.
Yes.
Can you also load an unsigned word there, even though you don't put like the U? Like it doesn't
What do you mean? For entire words, for 32 bits?
Mm-hmm.
No, there is only one instruction for that, because you don't have to do any conversion. You are taking 32 bits, writing 32 bits.
Okay.
The problem here is that we are taking 16 and writing 32.
Yeah.
So we need to do a conversion.
Yeah.
We need to know what we are going to put into the upper 16 bits. Mm-hmm. And there are 2 reasonable possibilities. One is to fill them with zeros, which is what the load unsigned does. And the normal signed load, what it does is replicate the upper bit, which is the next example, I believe. Yeah. I don't know why they are inconsistent. Anyway, this guy loaded the lower 16 bits as usual, but since the upper bit was a 1, it also replicated the 1 up to the end. Is it clear why we need to do that? No? Yes?
I just have a question. So the reason it's like all F's is because C is 12. So it just
Yes.
replicated the 1.
Yes, the upper bit, the bit number 15 or 16, whatever you want to call it, the signed bit. The problem is that, well, not a problem. If in memory you have this, and you are loading a single byte, that's a half word, which is 2 bytes, but it's the same idea. This can mean 2 things. It can mean 255 if it's a if it's an unsigned byte, or it can mean -1 if it's a signed byte. Whatever it is, the programmer knows. The machine doesn't care. For the machine, it's just 8 bits. Okay? If we are trying to put that into a register which is always 32 bits, we have to convert it to 32 bits. The bit pattern in 32 bits of this is this. And the bit pattern in 32 bits of this is this. So that's why we need 2 different instructions to load numbers. We have to tell the machine whether it's an unsigned number, and we have to extend with zeros always, or a signed number, and we have to extend with the sign of the number we are reading. Again, this is only for loads, and for loads which are smaller than the registers. So load of half, 16-bit numbers, or load of bytes, 8-bit numbers. If you are loading words, this doesn't make sense because it's always 32 bits, so you don't have to extend. If you are writing back to memory, this also doesn't matter, because if you are writing back to memory, you are taking whatever part of the register you want and writing that to the memory without doing anything more there. Okay, is this clear? No questions? Okay. Yes, so this was the explanation of this. The first part is just telling you that if you declared your array as bytes, then you will have to extend. Nothing much more here. Okay. This is an exercise on comparison. It's telling you if you assume the numbers are in choose complement, which is the usual thing. It depends. For example, FF, if you take it as a 16-bit number and you zero extend it, it becomes 255. But if you are sign extending it, it is still is -1. It's basically just to reiterate the same thing. This is what we have already explained. As I said before, it's important to know that the machine doesn't really know what's in the numbers. That's something you, every time you use them, you explicitly need to tell it. The numbers are not tagged anyway. The machine doesn't know what is that. It can be a signed number, an unsigned number, part of a string, an instruction, whatever. Okay, so this is what you have to do in the lab. This is the first exercise, since it's a fixed length list, and the length was 10, if I remember correctly. What you have to do is you need a counter, which you will count up and down whatever you want. Every iteration you compare to see if you have to continue or not. And then you read from whatever position in memory. You can do the address calculation every time, or you can just increment your pointer by 2 in this case. Okay? Yes?
In the lab, the last element in the array is the way they wrote it in the data part. They wrote it as 2 bytes instead. If you were to, when you read that, if you read a half word, it's going to read both those bytes.
That's right.
Okay.
Yeah, that's intentional. That's to drive the point home.
Okay.
And you, if you wanted to, you could write the entire array as 5 words, for example, and you will be reading first one half, first the other half. Okay. Again, the machine doesn't care. Memory is memory. You can fill it whatever you want. But yeah, that's the thing. Going back to that, the address calculation, there are 2 ways to do it. This is probably similar to what you would do in C, which is basically take an array, multiply by the element size, which is 2 in this case, because we are reading half words, add that to the base address, and read that address. There are simpler ways to do that. You can just increment your pointer address by 2 every iteration. That's probably quite a bit easier than doing the multiplication or the shifting every iteration. This just illustrates the iteration. The second variant, you have to watch out for zeros. There is a 0 in the middle of the array at position 7, I think, right? And you finish when you find it, basically. Nothing more to it. It's one more check. Apart from positive and negative, you have to look out for zeros. And there we finish. Yeah. And the third part is the most interesting part, so it's really not more difficult. Here you have a table with addresses and values. You have to process the value as usual, and then use the address to know where are you going next. Can everybody imagine what sort of instruction do you have to use for that? Does everybody know how to do that? More or less? No? Yes? How can you read an address for an address? Like, I'm reading from whatever I have in R4, and whatever is pointed to by R4 is an address. And I want to follow a single listed list with no data. Like, this is just a pointer which points to the next element, which points to the next element, and so on. So what will be the code for that? If the initial element is in R4, what do we need here? What do we put here, for example? Any ideas? I want to follow a linked list. Read a pointer, then read what it's pointed, what's that pointing to, and so on, forever. Let's assume it points back to the beginning, so we don't have any strange behavior. Yes. Yes. That's it. Done. That's all you need to follow a linked list. That's not the same you have to do there, because every element has 2 pieces. One is the actual element, and the other is the data. But basically, following the pointer to the next is as simple as this. Almost the same. You will have to do something slightly different, because the data and the pointer are not at the exact same location. So you will need to perhaps put something here, but you only need a single instruction at the end of the day. Okay? And yeah, that's just illustrating how we follow the address. I believe in your exercise, these two are swapped. First you have the data, and in the second position you have the address, if I remember correctly. Okay, we are going to do a simulation. This is the exercise, and this is part 1. We are not going to show the code for obvious reasons. Here in the simulator, like in the monitor program, hopefully you can actually go to symbols such as out negative. This is where the list is going to start. Can everybody see this? It's probably a bit small, right? I don't know if I can make it bigger. Let me try. Okay, so the list starts here. The list is supposed to be half words, I think. Just a second. Let's run the first iteration to see what happens here. Are we at the right place? Oh, negative. This is the positive. 0, 1. Let's run 2 more. Yeah, so we have processed the first 2 elements. In out negative, we have stored the first one, which is -1 from the list. This one over here, if you can see it on the right part, probably have to zoom this a little bit too. And in out positive, we are going to find the first one, which is 1, right there. Can you see it? I think we can visualize it as decimal for clarity. Yeah. This is what you will need to do to verify that your program is working. And the list, we can also see it in here. For the list, we have to define the data type as half words, because that's what we have in the source. And we have 2 per line, but you can see 1, -1, -2. Is it here? Yeah, -2, 2, 0, -3, 100, -100, etc. That's the list we have declared on our source file. Is there? Yes?
For part 1, what are the LEDs represent?
Oh, for all the parts, that code is written for you. It's just the number of elements you have processed.
Oh.
This means we are going to do the 3rd one now.
Okay.
We have done 2 already. What it does is read the old bit pattern from the LEDs, add 1, and then write it back. So it's basically a counter. When you are done, it's supposed to show 10. So liked, not liked, liked, not liked. That's it. We can keep processing numbers. You are counting the values into R3 and R4. That's the other compromission you have to do. You can, where are they? Sorry, into R2 and R3, you can check there that the number of positive and negative number matches what you expect. Let's run another iteration. We found another negative number. If we go to out negative, there is the -2. This list is in Word format, so we have to visualize it like that for it to make sense. So we have placed -1 and -2 in the negative list. The next one is 2, so it will go to out positive. If we continue, we will write a 2 in there, which is the new value we have in there. And our counters are 2 negative, 2 positive. And we keep going until we finish the list. 3, 3, 4, 4, 4, 5, and we are done. So we have 4 negatives, 5 positives, and that's it. And the numbers are here for the positive and in the other place for the negative. Is this clear to everybody what you have to do? It's as simple as that. This is part 1. For part 2, you will have to stop when you find the 0. This 0 over here. Of course, it's not valid to change the length to 4. That's not the solution. The 0 could be anywhere. And then for part 3, you have to follow the linked list, which you can see in memory. Right there. The first element is the value, the second element is the address of the next element. In this case is 98, which, sorry, let's change this to 1. So it's more clear. This tells us that the next element is at address 98, which incidentally is the very next address, which is this one. This is a -1. The next address is A0, which again is the next one, until we reach here, and it tells us that the next address is B8, which is no longer the next one. From here, we will have to go to here to find our next number. Sorry, I got lost. It's confusing. B8, this is a small negative number, and then the next element is C0, which again is the next one. And you keep following the list until your next address is a 0. Okay? We can run a few iterations if you want to, but there is no difference between this and the other ones. We are counting, and now we are done. We have processed 10 elements too, and the counter of positive and negative elements are here. 4 negative, 5 positive, and the output lists are like so. -1, -2, -3, -100, and one, 100, 15, 64, whatever. Using the simulator is very easy to verify that your program works correctly because you can see it running step by step. You can check the addresses in the registers, check in the memory window whether that address contains what you expect to. The simulator also checks for several programming errors you might have that the actual board won't tell you. For example, if you try to run data as code, or if you read from an unaligned address, or if you write to the wrong place, it will tell you. So it's a good idea to run it through the simulator just because it prints more diagnostic messages in general. The other thing is, when you look at the source code, you might be under the impression that the first pair is an element, the second pair is another element, the third pair is another element. But as we always say, the machine doesn't care. And at some point, you might find out that instead of going here, you go here in the middle. So this becomes your number, and this becomes your pointer. That's valid. That can happen, and that's something you have to solve. That happens, actually. So don't take every pair of words as a struct or as a class or whatever you want to. The machine doesn't care. Okay? As we saw in the previous lecture, the labels are substituted by the actual addresses when you compile this. And they might depend on the position of the code in memory. If you add more numbers to the other list, the values of the letters, the values of the labels are going to change. Okay? Like, I don't know if there was an example or yeah. At some point, you are expected to, one of the values you will put into memory is actually a label. So you will need to think what the value will become. Anyway, you will see that when you try to do the pre-lab. Any questions? Comments? Is everything clear? The code is not particularly complicated, what you have to do here. And the difference between the parts is like 3 instructions, maybe 4. It's very small. Once you have the first part done, the other ones should be pretty easy, hopefully. For the first part, the data is half words. For the second part is words. So make sure you change that, because otherwise you are going to see strange things. And I don't think there is much more. Yes?
If we have changed the R16 register for other temporary use, can we change the source code in the LED display part to fit?
Yes, yes. I mean, it would be easier if you didn't use R16 to start with, but yeah, of course you can. All the registers are the same, more or less. At least the lower ones are interchangeable. So yeah, you can change it. There's no problem with that. The LEDs are not really important for this lab. It's just a counter to see that there is progress. But to look at the results, you are going to have to use the debugger in the monitor program and look at the registers and the memory, because we don't actually show anything in the board. Anything else?